Welcome to Lesson 3, Sustainable Materials. Now that we've defined sustainability and learned about tools that can help us analyze sustainable packaging, let's dive into the sustainability aspects of materials and formats that we commonly find in packaging. Let's remember, no material is inherently good or bad. All materials have strengths and weaknesses. A sustainable packaging portfolio leverages the strengths of all the material types, enabling them to work in concert. Sustainability is a team sport. So let's start by discussing the basics of fiber, glass, aluminum, and plastic packaging materials. Fiber-based packaging is typically made from virgin wood pulp sourced from forestry and recycled fiber. The process begins with raw materials being pulped and mixed with water to form a slurry. This slurry is then refined to remove impurities and create uniform consistency. Next, the mixture is spread onto a moving mesh screen where water drains away, leaving behind layers of fibers. The layer is pressed and dried to form sturdy sheets of paper or cardboard. Depending on the desired product, these sheets may undergo additional treatments such as coating, cutting, and shaping before being assembled into their final shape. Common fiber-based packaging formats include cardboard boxes, cartons, and trays. Fiber can be folded and formed into a variety of shapes and sizes. We will dive into the life cycle performance later in this lesson, but the primary sustainability benefits of fiber-based packaging include being made from a renewable resource and being recycled at a relatively high rate compared to other substrates. Trade-offs include a lack of product visibility and the need for coatings and barrier layers when protecting products from moisture. According to the Recycling Partnership's State of Recycling Report 2024, nearly 23 million tons of fiber-based residential waste is generated nationwide annually. Fiber accounts for nearly half of the total amount of residential waste generated. The recycling rate varies by format type. The report cites a recycling rate of 32% for cardboard, 23% for mixed paper, and 8% for gable-top cartons. Fiber-based packaging can be compostable depending on the specific materials used and any coatings or treatments applied to the packaging. Packaging made from unbleached paper or cardboard without additional additives or coatings is often compostable and can break down naturally in a composting environment. However, some fiber-based packaging may contain synthetic coatings or additives for moisture resistance or printability, which can affect its compostability. Glass packaging is made by a process that involves several stages of heating, shaping, and cooling. It begins with raw materials extracted from the earth, such as silica sand, soda ash, and limestone, and recycled glass being mixed together and melted in a furnace at very high temperatures. Once melted, the glass is formed into its desired shape through methods like blowing, pressing, or molding. The formed glass is then gradually cooled in a controlled environment to strengthen its structural integrity. Finally, the glass packaging may be treated with coatings or decorations before being distributed. Common glass-based packaging include beverage bottles and jars. Glass packaging is known for its transparency, premium appearance, and barrier properties. It is a popular choice for preserving various products, from beverages to cosmetics. The main trade-offs with glass packaging include its heavy weight, brittleness, energy consumption in manufacturing, and dependence on mining activities for feedstock components. According to the Recycling Partnership's State of Recycling Report 2024, nearly 8 million tons of glass-based residential waste are generated annually from packaging nationwide. Glass accounts for 17% of the total residential waste generated. The report cites a recycling rate of 27% for glass bottles. One major limiting factor of glass recycling is the cost of transporting the cullet due to its heavy weight. Circular end-of-life options are limited to just recycling since glass is not compostable. Aluminum packaging such as cans and foil is manufactured through a multi-step process that begins with the extraction of bauxite ore, the primary source of aluminum. Once bauxite is mined, it undergoes refining to extract alumina, a white powder. Next, the alumina is smelted in a high temperature electrolytic process to produce pure aluminum metal. This aluminum is then cast into ingots and billets, which are rolled into thin sheets or coils in a process called rolling. These sheets are then further processed into the desired shape for specific packaging applications, such as cans or foil. The aluminum may undergo additional treatments such as coating or printing, depending on its intended use to enhance its properties or aesthetics. Aluminum packaging boasts several strengths, including excellent barrier properties against moisture, gases, and light. Its barrier properties ensure product freshness and shelf life extension. Furthermore, aluminum packaging can withstand high temperatures, making it suitable for hot and cold products. However, aluminum packaging does have weaknesses, such as its susceptibility to denting and scratching, which can affect its visual appeal. Additionally, the production process for aluminum packaging requires significant energy input, contributing to its carbon footprint. According to the Recycling Partnership's State of Recycling Report 2024, nearly 1.3 million tons of residential waste from aluminum cans are generated annually nationwide. Aluminum cans account for about 3% of the total residential waste generated. The report cites a recycling rate of 30% for aluminum cans. Circular end-of-life options are limited to recycling since aluminum is not compostable. Plastic is manufactured through a process known as polymerization, which involves the chemical transformation of raw materials derived from fossil fuels or renewable sources. The primary raw material for most plastics is crude oil or natural gas, which undergoes refining to extract key components known as monomers. These monomers are then chemically bonded together in long chains to form polymers. The resulting polymer can be further processed through methods such as extrusion, injection molding, blow molding, or thermoforming to create various plastic packaging products, including bottles, bags, containers, and films. Depending on the desired properties and applications, additives such as colorants and performance enhancers may be incorporated into the polymer formulation during manufacturing. Plastic packaging offers a range of benefits, including versatility, durability, and cost effectiveness. Its versatility allows for creating a wide variety of shapes, sizes, and forms to meet diverse packaging needs across industries. Plastic packaging is lightweight, which reduces transportation costs and energy consumption compared to heavier materials. Plastics provide excellent barrier properties, protecting products from moisture, gases, and contaminants, thus extending shelf life and ensuring product freshness. Plastic packaging is often shatterproof, reducing the risk of damage during handling and transportation. Its durability also helps prevent food spoilage and product waste. The main trade-off of plastic packaging is the challenge of recycling due to its limitless shapes and material combination. Plastic packaging, like glass and aluminum, is slow to degrade in the environment when waste is not properly managed. According to the Recycling Partnership's State of Recycling Report 2024, nearly 14 million tons of residential waste from plastic packaging is generated annually nationwide. Plastic accounts for about 30% of the total residential waste generated. Recycling rate for plastic packaging varies greatly based on material type and format. PET and high-density polyethylene clear bottles lead the way at 28% and 26%, respectively. Mixed plastics and films and flexibles from residential waste streams have limited recycling options. Biodegradable or compostable plastics are growing in popularity, but they are not currently mainstream solutions. Before we move on to discussing life cycle assessment comparisons from the various material types, let's briefly zoom out and compare end-of-life outcomes. Fiber packaging is the only mainstream substrate that can boast true biodegradability in most formats, where glass and aluminum packaging are not biodegradable. Plastic packaging can be made from biodegradable or compostable materials, but these solutions are not yet mainstream. One important note before we move on. Industrial composting sites typically do not accept packaging unless they are heavily soiled with a desirable product like coffee grounds, regardless of material type. Now let's focus on residential recycling. All material types have limited recovery due to constraints in the recycling access and participation. This chart highlights the highest rate of recycling per material type. These rates max out around 30%, regardless of material type. This points for the need to expand equitable residential recycling access and increase participation by building trust with consumers. Our next lesson will discuss strategies to design packaging to optimize its potential for recycling. However, before we move on to our next lesson, let's put what we learned in our last lesson about LCAs to use. I'm going to share a few recently published LCAs comparing common packaging material substrates. The first two studies I'm going to highlight compare global warming potential for packaging material substrates. The Imperial College of London published a study in 2020 that compared the carbon footprint of 500 milliliter beverage containers made from plastic, fiberboard, steel, aluminum, and glass. This study concluded that plastic and fiberboard had the lowest carbon footprint of the materials studied by a factor of 4x compared to aluminum and glass. McKinsey published a study in 2022 that examined the climate impact of materials in 6 different packaging applications: grocery bags, wet pet food, soft drink containers, fresh meat packaging, industrial drums, and soap containers. The study concluded that plastics have a lower greenhouse gas impact in 5 of the 6 applications studied. The industrial drum was the lone example of another material outperforming plastic in this study. The final study we will examine is a publication from TrueCost that compared plastics to their next best alternative. The study monetized and compared the impact of plastic used in consumer products and packaging to their next best alternatives across 3 aspects: damage to the health of humans and ecosystems, climate change, and damage to the oceans. Perhaps surprisingly, the study found that plastic has a much lower impact on these aspects than alternatives. Substituting plastics for alternatives would lead to 5.5 times more damage to the health of humans and ecosystems, 2.5 times more damage or impact on climate change, and 40% more damage to the ocean. In summary, every material commonly used in packaging has pros and cons. No material is inherently good or bad. Materials need to be selected in concert with each other to optimize sustainable packaging portfolios. So, how do we accomplish that? Our next lesson, Sustainable Packaging Design, will tackle material selection and much more. Stay tuned.